Namaskar, I am Dr. Meenakshi, Assistant Professor Mathematics, Sachoturam Government College for Women, Sampla. Today, the topic of my discussion is methods for solving first order ordinary differential equation, and it comes under numerical analysis paper for BA BSc 5th semester mathematics. Okay, there are various methods in this series that we can use to solve a first order ordinary differential equation, that is we can say first order initial value problem. Now in this series we will cover Taylor series method and our Rangakuta method. Just a minute. Okay, this is our Taylor series method. Here we consider the first order differential equation, that is dy by dx is equal to f of xy, and the value of y is given for a particular value of x, that is we suppose for x is equal to x naught, y is equal to y naught, and these type of problems we say these are initial value problems. Okay, now let y is equal to fx be the solution of this equation and such that f of x naught is not equal to 0. Now we will expand this f of x naught plus x minus x naught by Taylor series. We have come across Taylor series, Maclaurin series in our first semester under the paper calculus. Okay, we will apply same Taylor series method here. Now expanding this series y is equal to f of x naught plus x minus x naught by Taylor series about the point x naught, we get y is equal to f of x naught plus x minus x naught into f dash x naught plus x minus x naught square by factorial 2 into f double dash x naught plus so on. Now we can also write it as, because y is equal to capital X, fx is the solution of the equation, so we can replace f of x naught by simply y naught. So in equation 2 we have got y is equal to y naught plus x minus x naught into y naught dash plus x minus x naught square upon factorial 2 y naught double dash. This gives the value of the y for every value of x for which equation 2 converges. Now we put x is equal to x1 is equal to x naught plus h. What is this h? This is actually the interval of differencing, and for this particular value of x1 the corresponding value of y will be y1. So we get y1 will be equal to y naught plus h into y naught dash plus h square by factorial 2 y naught double dash plus h cube by factorial 3 y naught triple dash plus so on. Okay, next further we should see. Similarly, in this manner we can find the value of y2, y3 and so on, and at last we finally reach at y m plus 1. So the value of y m plus 1 will be equal to, if we compare from these results, you see here, if here it is y1, then on right hand side this is y naught. So in a similar way, if we see if it is y m plus 1, then on right hand side it will be ym. So we can write ym plus 1 will be equal to ym plus h into ym dash plus h square by factorial 2 ym double prime plus h cube by factorial 3 ym triple prime plus so on. Here ymr means this is the rth derivative of y corresponding to x at the point xm ym. So if we put these values of first, second, third and so on other derivatives, we can find the value of ym plus 1, and numerically this is the solution. Okay. Now in this method successive derivatives are used. So when it is not easy to find the derivatives easily, then this method is not so useful. So this is the main drawback. This is the drawback of this method. Okay. So finding the starting value of the application of my methods, we now use Runge-Kutta method and Milne-Simpson's method. So our next method for solving ordinary differential equations, particularly first order differential equations, is Runge-Kutta method. And this method also contains a series of methods we will see later. So the Taylor series method for solving differential equations numerically involves lot of labor in finding out the higher order derivatives. But in Runge-Kutta method, the calculation of higher order derivatives is not required. Okay. So this method has greater accuracy. So the method requires the functional values at some selected points and agrees with the Taylor series solution up to the term containing h raised to the power r, where r differs from method to method and is called the order of the method. So in these methods, the accuracy increases at the cost of calculations. So most widely used method is Runge-Kutta method of the fourth order, you can say. So first we will discuss Runge-Kutta method, or in short form we may call these as RK method. So first method is RK method of first order. Okay. Look here. Consider the differential equation. This is our first order differential equation and these are the initial problems. Okay. Now, by Euler's method, we can write y1 in terms of y0 as y1 will be equal to y0 plus h into f of x0 y0 is equal to y0 plus h into y0 dash. Okay. See here. Our function in first equation f of xy is equal to dy by dx, means first derivative of y. So we have replaced f of x0 y0 by simply y0 here, y0 dash. Now we have y1 is equal to y at x0 plus h. Because x1 will be x0 plus h, so y1 will be y at the value of x0 plus h. And again we expand this, that is y x0 plus h, by Taylor series. So we see that y1 will be equal to y0 plus h into y0 dash plus h square by factorial 2 y0 double dash plus h cube by factorial 3 y0 triple dash plus so on. So here we can see that Euler's method agrees with the Taylor series method up to the term containing h. You see that only first two terms of these match with the Euler's method. So Euler's method is the Runge-Kutta method of the first order. So Runge-Kutta method of first order, or you can say Euler's method, both are same. And we have discussed earlier methods earlier, Euler's method earlier. Now next we will discuss Runge-Kutta method of second order. Okay. In this method, we will use Euler's modified method. So this is our Euler's modified method, and the expression is, what is the expression in Euler's modified? You see here, y1 is equal to y0 plus h by 2 into function at x0 y0 plus functional value at x0 plus h and y1. So this is our Euler's modified method. Now in right hand side, if we put y1 is equal to y0 plus h into f of x0 y0, then we get the expression as this, that is y1 is equal to y0 plus h by 2 into f0 plus f of x0 plus h, comma y0 plus h into f of f net. So simply we have replaced y1 by the value. Now we expand this by Taylor series. So left hand side is simply our y1, on right hand side y0 plus h by 2. In square bracket we have f0 plus, next expression is f of x0 plus h, y0 plus f of f0. So we apply or expand only this term by Taylor series method. So if we apply Taylor series method here, we find that this will become f of x naught y naught plus, here increment is h, so we can write h into curly f by curly x at x naught plus h into f naught curly f by curly y at x naught plus other higher order terms of h. So after simplification, we see that the terms under the bracket becomes h into f naught plus h into f naught plus h square, and again bracket curly f by curly x naught plus f naught into curly f by curly y naught and other higher order terms. So we see that finally the value of y1 comes out to be y naught plus h into f naught plus h square by factorial 2 d by dx of fxy means double derivative. So we can write it as y naught double dash plus order of h cube. Here we have replaced curly f by curly x plus curly f by curly y dy by dx, that is this term, by df by dx. So we use the notation this here in this step. So from here we find that y1 is equal to y naught plus h into y naught dash plus h square by factorial to y naught double dash. This is the expression for the Taylor series method. So if we compare both these results in 4 and 5, we see that Euler's modified method again agrees with the Taylor series solution up to the terms containing h square. So we can say that Runge-Kutta method of second order is same as our Euler's modified method. So the expression for this becomes y1 is equal to y naught plus 1 by 2 k1 plus k2. So we are to learn this formula and we will use this formula in our calculations, and the value of k1 is h into f of x naught y naught and the value of k2 is h into f of x naught plus h y naught plus k1. So this is our Runge-Kutta method of second order. Now next comes Runge-Kutta method of third order. So we will discuss this method here. Again see, as we have proceeded earlier, we see that Runge-Kutta method of third order agrees with the Taylor series solution up to the terms containing h cube. So from the earlier two articles discussed, that is Runge-Kutta method of first order and second order, we can say this Runge-Kutta method of third order, this agrees with the Taylor series solution up to the terms containing h cube. So to find the increment of k of y corresponding to an increment h of x by RK method, we proceed as follows. Now k1 will be equal to h into f of x naught y naught, k2 will be h into f of x naught plus h by 2 y naught plus k1 by 2, and k3 will be equal to h into f of x naught plus h y naught plus k dash. Here k dash is equal to h into f of x naught plus h y naught plus k1, and again combining these values we get the expression y3 is equal to y naught plus 1 by 6 into k1 plus 4 k2 plus k3, and this is the expression for Runge-Kutta method of third order that we will use in our problems. Okay, next move on to the Runge-Kutta method of fourth order, and simply this is called Runge-Kutta method, and this is the most commonly used method and often referred to as Runge-Kutta method. So here to find the increment k of y corresponding to increment h in x, so we proceed the following steps. Here we find k1 will be equal to h into f of x naught y naught, k2 will be equal to h into f of x naught plus h by 2 y naught plus k1 by 2, k3 will be equal to h into f of x naught plus h by 2 y naught plus k2 by 2. Notice this here k1 by 2, and in k3 it is y naught plus k2 by 2, and k4 will be equal to h into f of x naught plus h into y naught plus k3, and finally the value of k will be 1 by 6 k1 plus 2 k2 plus 2 k3 plus k4. So the Runge-Kutta method of fourth order will become y1 is equal to y naught plus 1 by 6 into k1 plus 2 k2 plus 2 k3 plus K4, and this is the formula for solving the problems by using Runge-Kutta method of fourth order, or you can simply say by Runge-Kutta method. So these are the expressions or derivation of formula of Taylor series method and Runge-Kutta method of first order, second order, third order and fourth order. Now we will solve the problems based on these formulas. So look here, our first problem is we are to solve the differential equation, and differential equation is dy by dx is equal to x plus y, and here we are to solve this differential equation using Taylor series method, and we are to start from x equal to 1, y is equal to 0, that is these are the values of x naught and y naught, and we are to carry on to x is equal to 1.2. So we are to find the value at x equal to 1.2, and we are to take h as 0.1, that is we are to take the gap between conjugative intervals as 0.1, and again in the last we are to compare the numerical solution obtained with the exact solution. So this is the problem, and here we are to solve this particular problem by using Taylor series method. So our given equation is this, dy by dx is equal to x plus y, and here x naught equal to 1, y naught equal to 0. So our function is f of xy, that we can say this is x plus y, and it is very simple to find the derivatives of this function. So we can apply Taylor series method here. So first fxy means that is equal to dy by dx, so we are given the value of first order derivative is x plus y, so y dash is equal to x plus y, we can write this. Now again differentiating this expression on both sides with respect to x, so we get y double dash as 1 plus y dash, now again derivating y triple dash will be equal to y double dash, and y fourth will be y third, and so on. So we calculate it up to order 5. Now we are to find the values of these particular derivatives at our initial points, and our initial point is x naught equal to 1 and y naught equal to 0. So we replace the value of x by x naught and value of y by y naught in these expressions, and we find that the value of y naught comes out to be 0, value of y naught double dash that is 2, y naught triple dash 2, and fourth derivative 2, and fifth derivative also 2. So we have find these values. Now we write the expression of the Taylor series. Now Taylor series is y1 is equal to y naught plus h into y naught dash plus h square by factorial 2 y naught double dash plus h cube by factorial 3 y naught triple dash plus h4 by factorial 4 y naught fourth order derivative plus h5 by factorial 5 fifth order derivative at y naughts. Okay, plus so on. So we have find these particular values, so we can put these values in this formula, and after calculation we find that the value of y1 comes out to be 0.110, and we have approximated this value. Now this is the value of y1, that is at x1 equal to 0.1, but we are to 1.1 you can say, but we are to find the value of the function at x is equal to 1.2, that is corresponding to 1.2. So for corresponding to x1 we have find the value of y1. Now we are to repeat this procedure again, and these are the again the higher order derivatives. Now we are to find these particular values at x1 y1 you can say. So by replacing the value of x by x1 and the value of y by y1, we find the particular values at y1 dash, y1 double dash, triple dash, fourth order derivative, fifth order derivative as this, and again putting these values in our Taylor series method, we find that the approximate value of y2 comes out to be 0.242. So the solution of the particular problem, that is the value of the function at 1.2 is 0.242. So this is our numerical value that we have found by using the numerical method, that is Taylor series method. Now we will find the exact solution of this ordinary differential equation. Now we have seen that there are numerous methods that we have used in our class 12th for solving a ordinary differential equations, that is homogeneous method, linear equation, variable separable you can say. So we will see or investigate or examine what type of this equation is and which method we can apply for solving it directly. Okay, look here. Now our differential equation is dy by dx is equal to x plus y. So we cannot solve it by simply variable separable you can say, or homogeneous method. I think it is not so easier to apply here. So we take y on left hand side, so the equation becomes dy by dx minus y is equal to x, and we compare this with dy by dx plus py equal to q, which is a linear differential equations, and here p and q must be the functions of x. So we see here the value of p is minus 1 and the value of q is x. So these are the functions of x. So this is a linear differential equation which satisfies the given conditions. So we first find its integrating factor, and the formula for finding the integrating factor is e raised to the power integral p dx, okay, exponential of this. So we put the value of p and we find that integrating factor comes out to be e raised to the power minus x, that is exponential of minus x. Now the solution of this type of equations will be y into integrating factor is equal to integral q into integrating factor plus constant of integration. So we simply put the value of integrating factor q, and again by applying integral techniques we find that the solution comes out to be this, and we are to find the value of y. So we multiply both sides by e raised to the power x. So here in equation 1 this is our corresponding solution, but we see that it includes the constant c. So in it we are to find the value of c. So for this we use the initial conditions. And what are the initial conditions? Initially we are given that at x equal to 1 y is equal to 0. So we use these values here to find the value of the constant, and that comes out to be 2 by e. Now again putting this value in equation 1 we get the value of y as this, and when we substitute x is equal to 1.2, because we are to find the value of this y at particular point, that is 1.2. So if we replace x by 1.2 we find the value of y as 0.2428. So this is our exact value, and this was our numerical value that we have found by using Taylor series method. So in this way we can see that we can apply Taylor series method to solve a particular problem. In the next problem we will also discuss how to solve a particular problem by Taylor series method. So our next problem is we are to obtain the approximate value of y at x equal to 0.2 for the differential equation. Here differential equation is dy by dx is equal to 2y plus 3e raised to the power x. So this becomes our function. Now initial values are x not 0, y not 0, and again we are to compare the numerical solution with the exact solution. Okay, look here, this is our given differential equation and these are our initial conditions. So first of all we find the higher order derivatives, then we will find these values at the initial value points. Now we will use Taylor series method. This is our Taylor series formula. Now we will substitute these particular values here, and when we put x is equal to 0.2, because we are to find the value at x is equal to 0.2. So we substitute x is equal to 0.2 in this expression and we find that the value comes out to be 0.8110. Now we will find the exact solution of this equation. So again we see that this is a linear equation of the form dy by dx plus py is equal to q, where p is equal to minus 2 and q is equal to 3 into e raised to the power x. Now we first find the integrating factor by using the formula, and that solution will be like this. And if we solve this we find that this is our solution. Now multiplying again both by sides by e raised to the power 2x. So this is our solution, and by substituting the initial values we find the value of the constant to be 3, and if we put the value of c in this equation then this is our solution. Now we substitute x is equal to 0.2 because we are to find the value of the function at 0.2. So we substitute the value in this. So we find that at this point the value of the function comes out to be 0.8113. So this is our exact value, and we have also find this numerically, and that comes out to be 0.8110. So in this way we can apply Taylor series method and also find the solution in a exact way or numerically. Now next comes the problem by Rangakuta method. So next problem is apply Rangakuta fourth order method. We are to apply fourth order method here to find an approximate value of y when x is equal to 0.2, and it is given that dy by dx is equal to x plus y, and these are our initial values. Okay, so this is our initial value problem. These are the initial conditions. Now we take h 0.2. So for Rangakuta method of fourth order, first we have to find the values of k1, k2, k3 and k4. So what is k1? K1 will be h into f of x naught y naught. Here function is given as x plus y. So this expression will be 0.2 into x naught plus y naught. Simply we put the value of x naught and y naught again, and we find the value of k1 to be 0.2. Now we will find the value of k2, and the value of k2 will be equal to h into f of x naught plus h by 2, y naught plus k1 by 2, and this comes out to be 0.24. Now next we will find the value of k3, and k3 will be find in the same way, that is h into f of x naught plus h by 2, y naught plus k2 by 2, and we know the value of h, x naught, y naught and k2. So we simply substitute these values in this expression and find the value 0.2440. And finally the value of k4 will be equal to h into f of x naught plus h, y naught plus k3. So again substituting the values, we find the value of k4 as this, and finally by Rangakuta method of fourth order, our k will be equal to 1 by 6, k1 plus 2, k2 plus 2, k3 plus k4, and y1 will be equal to y naught plus k. So we put the value here. So this is the value of the function corresponding to x is equal to 0.2. So in this way we can apply Rangakuta method of fourth order to solve a particular problem. So next move on to the next problem. Our next problem is we are to given, this is our first order ordinary differential equation, that is dy by dx is equal to 1 plus y square. So this is our function, and initially x naught equal to 0, y naught is equal to 0, and we are to find the value of function at 0.2, 0.4 and 0.6. We are to find the value of y at these 3 points. Okay. Now we take the value of h as 0.2. Now we have started from 0. So the next value corresponding to x will be x naught plus h, and that comes out to be x1. So our x1 will be 0.2, x2 will be 0.4 and x3 will be 0.6, because we have considered h as 0.2. So first we will find the value of the function at 0.2. For this we first find the value of k1, and k1 will be equal to h into f of x naught y naught, and this comes out to be 0.2. Now for k2, h into f of x naught plus h by 2, y naught plus k1 by 2, and this comes out to be this. So the value of k2 is 0.202. k3 is equal to h into f of x naught plus h by 2, y naught plus k2 by 2, and again substituting the values, we find that the value of k3 comes out to be this, and again we can find the value of k4 as this. So we have find k1, k2, k3, k4, and the value of y1 will be equal to y naught plus 1 by 6 k1 plus 2, k2 plus 2, k3 plus k4. So this is the value of y1, that is this is the value corresponding to x is equal to 0.2. But we are to find two more values, that is corresponding to 0.4 and 0.6. So to compute these values, we will now use the values of x1, y1. So our k1 will be here h into f of x1, y1. You see that when we find the first approximation, we will use the values at x naught, y naught. But here we will use the value of x1 at x1 and y1 simply to find the values of k1, k2, k3 and k4. So k2 will be equal to, in the same way, h into f of x1 plus h by 2, y1 plus k1 by 2. So this is the value of k2. Now the value of k3 is h into f of x1 plus h by 2, y1 plus k2 by 2. So this is the value 0.2195. Again we will find the value of k4, and the value of k4 is h into f of x1 plus h, y1 plus k3, and the value of k4 comes out to be 0.2356. And finally our second approximation will be y2 is equal to y1 plus 1 by 6, k1 plus 2k2 plus 2k3 plus k4, and we have find all these values. So we put these values here to find the value of the function at 0.4. So this is the required value. So now we have computed the value of y2. Now we are to again find the value of y3, that is at 0.6. So we will use the values of x2 and y2 for solving these. So when we will find k1, we will write it as h into f of x2 y2. The value of k2 will be h into f of x2 plus h by 2, y2 plus k1 by 2. Or simply then we will replace the function. What was our function? 1 plus y square. So this will be 1 plus y. Replace y by y2 plus k1 by 2. So this is y2 plus k1 by 2 square here. Okay. Now the value of k3 will be h into f of x2 plus h by 2, y2 plus k2 by 2. 0.21 plus y2 plus k2 by 2 square, 0.21 plus this y1 square, and this is simply k4 and y3. Okay, so this in this way we can find the value here. Our next example is Rangakuta method to solve this particular problem. So this is the method to solve this particular problem. 10 dy by dx is equal to x square plus y square, and y at 0 is equal to 1. So here we are to take the value of h as 0.1. So this is our given differential equation, and this is dy by dx is equal to f of xy. So these are our initial conditions, that is x0 and y0. Here we take h as 0.1. So we see that the value of x1 will be 0.1, x2 will be 0.2, x3 will be 0.3, and x4 will be 0.4. So first we are to find the value of y1. For this we will use the values of x0 and y0. So you see k1 will be h into f of x0 y0, and this is the value k2, k3 and k4. So by using these formulas and simply putting the values, we can find these values, and finally we find the value of k, and so our y1 will be equal to y0 plus k. Again we will find the value y2. So again we will find the value of k1, k2, k3 and k4, and again we compute the value of k as 1 by 6, k1 plus 2, k2 plus 2, k3 plus k4, and the value of y2 will be y1 plus k. Again we will find the value of y3, and for this we again find the value of k1, k2, but here we will use the point x2, y2. Okay, it's clear. Now find the value of k3, and now k4. This is our k4, and again by using these values we find the value of k as 1 by 6, k1 plus 2, k2 plus 2, k3 plus k4, and finally y3 will be equal to y2 plus k. So we find the value of y3. Now we are to compute the value of y4. For this we will use the values of x3, y3. So first of all again find the value of k1 as h into f of x3, y3, and it comes out to be 0.0115. Next value is k2, h into f of x3 plus h by 2, y3 plus k1 by 2, and it comes out to be 0.012. Next value is k3 and h into f of x3 plus h by 2, y3 plus k2 by 2, and it comes out to be 0.012. And next k4, and this is h into f of x3 plus h, y3 plus K3, and after putting the values we find that this value is 0.0125. So we have seen that we have computed all the values correspondingly at 0.1, 0.2, 0.3 and 0.4. So this is Rangakuta method. I think this is understood to you that how can we solve a particular problem by applying a particular Rangakuta method. In these problems we have used Rangakuta method of fourth order because this is the most common method that is used. So we have discussed Taylor series method and Rangakuta method here. So I think this is the topic covered by using Taylor series method and Rangakuta method of various orders we have discussed, and we have also discussed their numerical problems, and I think this is all up to now. Thank you very much.